Produce another matrix before we finish the class. Unitary matrix. This is very important. Okay? So why? Just give you a definition. I have a matrix, right? I can call it A, I can call it H, but now I call it U. This is just a name. If U dagger equals to U minus, what? How about Hermitian matrix? What is the definition? If I call it U. U dagger equal to what? To U. That is Hermitian matrix. But here is U dagger equals to U minus, which minus one, which is inverse, right? Which means what? Which means, or you can say U dagger U equals to identity matrix, or multiply U at both sides, or U dagger equals to I. It doesn't matter, they commute, okay? Because now I multiply on the left side, right? Then they are called the unitary matrix. Why unitary is so important? Because if you apply unitary matrix to a space, to some vector, it will preserve the inner product of two vectors. It means the relationship between two vectors is still the same, which is very good, right? Just like this building's relationship to let's say the Duncan Hall. The world is rotating. If when it is rotating, they get closer and crash, or they get farther apart, that this world is very weird for us, right? So here what it's trying to say, I have two vectors, means two states. Their inner products, their relationship doesn't change no matter how you transform it, if you use the unitary transformation. So that is a very important transformation, right? So let's try to see why. For example, this is also a proof, right? This is also a proof. Try to prove that it preserves. So I have two vectors. I call it F and G. Okay? Now, I apply a transformation U. So it becomes F dash equals to UF. Right? I transform it, I rotate it. The other vector is G dash equal to UG. Is this okay? What I'm trying to say that U were F, now apply U, apply transformation, unitary transformation, rotate U, then you become F dash, right? So I was standing here, a vector, now you rotate me by 90 degrees, I become someone laying on the floor. That is a, let's say, unitary transformation, right? So you were standing, let's say you were lying on the floor, we try to do a rotation 90 degrees. So now I lie on the floor, you are standing up. The angle between us still 90 degrees. The inner product between us is still the same. You hope that this will happen because you are not really rotating, maybe just observer rotating himself or herself. Right? The physics should not change if I try to rotate myself to see in a different angle, right? The real physics, right? So this is what we have. So before rotation, right? Before transformation, we have the inner product, which is FG. Correct? After transformation, what is the inner product? By definition. F dash, G dash. But what is F dash? Maybe we can come here in bra. What is F dash here? If this is the cat, then its bra's form is what? Do you still remember what we learned earlier? Matrix times a cat, its bra version is what? is bra times U dagger. Do you recall this equation we learned last time? Maybe you forgot, but you should feel that it makes sense. Because U times column vector is your image must be bra for sure, right? Because cat must be bra. But now become a row vector, so you must put the matrix on the right-hand side. And then because we're doing dual space, it's his dagger, right? Transpose with adjoint. So this one you need to remember. Okay, so because of this, then what do I have? This become Fu for F dash. How about G dash? What is G dash? UG. I made FU dagger, no one point out the mistake. UG. Right? This is F dash. And this is G dash. Correct? But what is U dagger U? If it is unitary, what is U dagger U? Yes, very good. Identity matrix. And what happens if you apply identity matrix to anything? Doesn't change anything, right? So this is equal to Fg. So inner product unchanged after unitary transformation. All quantum gates need to be unitary. Okay, so in the future, when you do the quantum computing, all gates need to be unitary. Okay, that's why this is important. Any questions? Because you also need to reverse back. You're right. And you can see that unitary must have an inverse also. Right? Because unitary matrix means U dagger equal to now you does it need to be a square matrix? I'm not sure actually, but we only deal with square matrix here in quantum computing. Yeah, I need to check. I forgot this field. Yeah. Yeah. Any other questions? I won't go to a new slides. Any other questions? If not, then I will stop here. Say again.